Welcome to the Infermath channel. The first course we will look at is probability. This mathematical discipline has developed from random games. To understand it better, we will do some probabilistic experiments. We can do that using statistical packages. The package we will use is called R. R is an open source project. It means that it is created by the community of programmers and is available for free. In this course, we will not only learn probability theory, but also statistical programming. Therefore, it is important that you write the R code yourself. If you don't have it yet, please download R using the link in the description of the video. We will start the probability course with discrete random variables. You can think of a random variable as a game. Variable means that there are several possible outcomes. Random means that we don't know the outcome before we play. And discrete means that we can count the number of outcomes. The simplest discrete random variable is a fair coin toss. In this video, we will use R to generate it. Let's go. We are in the command window of R now. The fair coin toss is a random variable that has got two outcomes, heads and tails. Each of these outcomes has got the same probability. So probability of heads is equal to probability of tails, which is equal to 0.5. In R, we can comment out the text using hashtag. Then it will not be executed. So how can we translate this random variable into R language? Computers are binary machines. They communicate using zeros and ones. Let's then call our variable x, and let's agree that x equals 1 represents heads and x equal 0 represents tails. So then we have probability of heads equal to probability of tails, and it's equal to 0.5. So how can we generate such a random variable? The simplest random variable that R and other programming languages can generate is a uniform random variable. Uniform random variable can take all the values between 0 and 1 with equal probability. To generate a uniform random variable in R, we are using runif function for random uniform. The function takes one argument, which is the number of draws from the uniform distribution that we want to generate. So if I type in runif1, the R will generate one number between 0 and 1. If I type it again, I will see a different number between 0 and 1, which is what we want, because we want those numbers to be random. To call the previous commands in R, we can use arrows. Arrow up will call the previous command. Let's see if runif function really generates the numbers between 0 and 1 by increasing the number of observations to 10. We see that in 10 draws, we see some numbers which are close to 1, like this one, and close to 0, like this one. Also, there is no number outside this interval. So we are happy with our runif function. It seems to really generate numbers between 0 and 1. We will study uniform random variable in more detail when we look at continuous random variables. For now, we will use it to generate our fair coin toss. How can we do this? It is very simple. What happens if we round our uniform random variable? If the number is higher than 0.5, it will be rounded up to 1. If it's lower, it will be rounded down to 0. So we see here that bunch of zeros and ones are generated. But is the probability of getting zeros and ones the same and equal to 0.5? To check that, let's generate more of these random variables. So here we have a sample of 10 different draws, and in the sample of 10 we have 5 zeros and 5 ones. So this is exactly what we wanted. However, it's not always the case. Here we also have 5 ones and 5 zeros, but here we only have 2 ones and 8 zeros. This is what we expect. After all, the samples that we are drawing are random. But how can we check if the probability of getting zeros and ones in each single individual draw is equal to 0.5? To get the percentage, we just need to sum up all the observations. This will give us the number of ones in 10 draws, and if we divide it by the number of draws, which is 10, we're gonna get the percentage of ones in our sample. So in this case, 60% of all draws are ones and 40% are zeros. We can do it in one step just using mean function, which will do precisely that. So sum up all the observations and then divide by the number. So this time 70% of the observations were ones. Let's generate a big vector of round uniform random variables. So let's say that our sample size, let's call it n, is equal to 1 million. We can write it like this, 10 to the power of 6. So now let's generate this vector. If I say r like result or random is equal to round unif of million, it's going to generate a vector of 1 million zeros and ones. Let's see what would be the average of our vector if we look at first 100 observations. To do that, we do index. We say that we want to look at vector r and observations starting from 1 to 100. We were quite lucky because here we got straight to the right answer, which is 0.5. What if we increase the sample size 100 times? We are getting something which is also fairly close to 0.5. How about if we take all the vector? To do that, we just say calculate the mean of R. We are getting a number which is really close to 0.5. We are happy. Our method generates zeros and ones with probability of 0.5. It is quite intuitive that as our sample size goes to infinity, our sum of ones divided by the size is converging to 0.5. In mathematics, this convergence is called Borel's law of large numbers, after a French mathematician, Émile Borel. This is the first law of large numbers that we're going to encounter in this course. It applies not only to fair coin toss, but also to more general case, when probability of heads is equal to p, which is a number between 0 and 1. We call such a general case a Bernoulli random variable, and we will examine it in more detail in the next episode. In the description of the video, you will find the R code that was used in this episode. I hope you enjoyed that, and we'll see each other in the next episode.